So in the first introductory lesson we mentioned electric potential and potential energy. So the idea of this little session is to really go into detail what we mean by potential and potential energy of a field. So the idea is, can we judge the properties of a field by just looking at a field diagram? So how much can you actually learn about the field by just thinking about what you can see in terms of the field lines? What do we mean by the potential of a field? We should already know that, but we'll revise it. And what is the potential difference of charges moving in a field? We'll consider that, and we can work out how we can do some quick calculations based on the differences in energy of moving charges in a field. So here we go then. Let's just think about electric potential. Here we've got two charges, x and y. If we bring x towards y, we can start to think about what's going to happen when we're doing that. Work is done to move a charged object x towards another charged object y with the same charge. So if both of these are positive, x and y are both positive, for me to push x towards y, they're going to repel, so I will have to do some work. The field of y causes a force of repulsion to act on x, and the field of x causes a force of repulsion to act on y, so work's got to be done to overcome it. We say that the potential energy of x increases as it is moved towards y, and we need to say from a particular point in space, so we're going to call that point in space infinity. So as we come from infinity, then the potential energy of x is going to increase. So what do we mean by potential? We've met potential in our study in year 12 of electricity, and potential does mean work done per unit charge. So this quite literally is, how much work do I have to do on each unit of charge to get it from a particular point in the field to a new point? And in our case, we're thinking from infinity to that point. Let's define, to make life a bit easier, let's define that at infinity, when we are an infinite distance away from y, we would say that the potential energy of x is 0. So it's 0 at infinity, and then the moment we move closer to y, it starts to increase. And we know from previous studies the unit of potential is the volt, because it's defined as the work done per unit charge, which is E over Q. So it's 1 joule per coulomb. So let's do a little bit more of a detailed analysis. We've defined zero potential at infinity, and we know that there's going to be attractive and repulsive forces involved, so we've got to consider the possibility of positive and negative values for energy. So here we have a positive charge plus Q. We're at infinity, and we're going to move it towards our charge of plus Q in the middle here. So our first scenario is bringing a positive charge Q from infinity towards the fixed positive charge large cap uppercase Q. We've got to do work, so they're going to repel. So the energy, the work that we put in is stored. Remember, we can't sort of destroy energy. It's going to be transferred from one to another. So the work that we have to do on Q gets stored as electric potential energy in Q. So it's going to increase. It starts at 0 and it increases. So it's 0 here, and the closer we get to Q, it increases until we get to Q, where it hits its maximum value. Let's do exactly the same, but this time we're going to do it with a negative charge. So here's our negative test charge, minus Q, and we're going to bring it towards plus Q. Now the first thing to realise is that it's going to be 0 at infinity, just like before, but what's going to happen, they're going to attract. So as they attract, we're going to need to sort of do work to separate them. We haven't got to put work in. Effectively, we're taking work out, or we're removing energy. So we would say that energy is being transferred out of the test charge minus Q. So it's going to decrease. So the energy of the test charge minus Q is going to decrease. We've got to put work in to separate them. So therefore, it's a negative energy value. So if we define it for a positive test charge Q, remember in electric fields we always define things in terms of a positive test charge. For a positive test charge Q placed in a position in an electric field where its electric potential is E, EP, the electric potential V of the field at that point is given by V equals the potential energy divided by the charge. So this quite literally is how many joules per coulomb of charge. This is what we mean by potential. It's the joules per coulomb of joules of energy per coulomb of charge. If we rearrange that and put EP equals VQ, this is our formula for electric potential. EP equals VQ or QV. Can we define work done? Well, if we move this test charge plus Q and we move it from a position where the potential is V1 to a position where the potential is V2, then our work done is still going to be QV because it's a measure of energy, so it's a change in potential. And the change in potential comes about because we move our charge through two different potentials. So the change in energy is due to a change in potential. So our formula will be the work done, or delta W for a change, is equal to the charge multiplied by the change in voltage, or delta V. So work done equals Q delta V. A quick question with a little graph on this. This is quite useful, hopefully. An electron in an electron beam is accelerated from a potential of -50 to 450 volts. Calculate the potential energy of the electron at -50. Well, the potential energy at -50 is going to be Q times delta V. Q is -1.6 times 10 to the -19 multiplied by the voltage -50 gives us a positive energy. So it's got a positive value of energy when it's on, when it's at the -50 volts plate. What's happened when it's hit the plus 450 volt plate? Well, we've now got minus, so that it's Q is minus, that's the charge on the electron. We've got a positive plate, plus 450. So if we multiply 1.6 times 10 to the -19 times 450, we get an answer of -7.2 times 10 to the -17. So here we can see that it's gone from a positive value of energy to a negative value of energy. So the total change, you could work out the difference between these. What I've done is just gone -1.6 times 10 to the -19 times 500, which is my delta V. So the total change in energy is to do with the change in potential. The change in potential is from -50 to plus 450, which is a change of 500. So 1.6 times 10 to the -19 times 500 gives us our answer. Sometimes more useful to think of this in terms of a graph. If we plotted a graph of the potential energy of the electron, I've put my two values on here. This is my positive value of +8, calculated in part A. This is my negative value of -7.2. I know the scales aren't accurate, but it'd be, it's okay just to draw a quick sketch graph like this. We would see that the energy of the electron reduces from its highest value down to 0 at some point between these two plates, and then it's going to go even more negative, so it will reduce down even further to its minimal value at the 450 plate. So at this point, the negative electron is being repelled away by the negative plate, so it's got a positive potential energy here, but at this point the negative electron is being attracted to or accelerating towards the positive plate, so it's got a negative energy here. So the energy is swapping from positive down to negative. Okay, a little quick reminder of equipotentials and potential gradients. Equipotentials, we said, were lines of constant potential. Hopefully now you'll know a little bit more of what we mean by a potential in a field. There's no work done if you move a charge along an equipotential. So if I take a charge, and in this diagram here, if I move the charge around this circle, then I am doing no work on that charge. This is similar to walking around a hill. If you imagine this is a hill, and if you've studied geography, if you've got contour lines, if you walked around a hill, this is like a mound where its highest point is the top here, and then it gets lower and lower and lower. If you walk around a line that doesn't change in height, then your gravitational potential energy would not change. You would have to do no work. This is exactly the same concept with moving along an equipotential in an electric field. The electric field lines cross equipotentials at right angles. We've looked at that before. The potential gradient at any position in an electric field is the change of potential per unit change of distance. So we could look at the gradient. If this was a slope, we could look at the gradient of the slope, and in the same way we can look at the gradient of the electric potential. And the gradient of the electric potential here, you can see it's not as much in this area, but as it goes towards the positive charge, it starts to increase rapidly. So this would be like going up a hill. This would be a sloping uphill, because what the potential gradient means is it's the change of potential per unit change in distance. So here in this distance here, we've got more of a change of potential than say in this distance here. So what you can do, you can look at the potential gradient and you can gauge it in looking at how close the equipotentials are. As the equipotentials get closer and closer, then you can see that the potential gradient is increasing. If we look at a uniform field, we've mentioned this before in lesson 1, we can see that here the equipotentials are evenly spaced, so this would be an evenly spaced or an even gradient, a constant gradient. Let's look at that in a little bit more detail. This is the uniform field again. The equipotentials are parallel to the plates. It increases as distance from the negative plate increases. So this would be, for a positive charge, this would be the minimum value of energy, this would be the maximum. So if we look at a graph of that, this is distance from the negative plate, remember. So as I move across the plates in this direction, my potential increases. So my gradient is a constant because the equipotentials are evenly spaced, and it's increasing in this direction. Now, interestingly, potential gradient is increasing in this direction, whereas our field strength was in this direction. So the potential gradient is in the opposite direction to the field. The potential increases in the opposite direction to the electric field. So if you remember, the electric field strength E is directed from the positive to the negative plate. There's the diagram. The electric field is positive to negative and is equal to V over D. The electric field strength is the negative of the potential gradient because the potential gradient increases this direction, and the gradient of this line would be V over D. Finally, just a quick look at non-uniform fields. If this is sort of quite a complicated field diagram, you've got two positive charges. The field between them is shown here. The red lines are showing the direction of the field, and the potential gradient you can see is increasing quite rapidly here. You can almost see this as two hills next door to each other. This diagram's quite nice. If you had to climb this hill, then if you're a geographer, you'd say, we're not going to climb this side because it's very steep. We're going to climb this side because it's not as steep. This would be an aerial view. This could be what the hill looks like. It's not as steep here, whereas here it's much steeper, so you wouldn't want to climb that face. And this is the same in terms of these potentials. The electric potential is increasing rapidly here, but if you look here, it's increasing less rapidly because the spacing of the electric potentials is much further apart.